Hi everyone watching the recording. This is Spirit AI workshop. Hi again.
How long should we wait for people to come in?
I think we could just get going. Yeah, I think we could get going.
Okay, is it okay if I ask people to turn on their videos?
Yeah, could people, you don't have to, but if anyone could turn on their videos, that'd be really awesome.
Yeah, just so I don't like stare at people's names. That would be great. It's just better if I know I'm talking to real human beings, but don't feel pressured.
Yeah. That's it. Anyone else? We see two black screens interested?
Okay, so I'm gonna start. Thank you guys for everyone who has shared their screen so far. Okay, so first, for a little bit of context, I'm from Spirit AI. It's a company started by some Stanford students, and now Stanford students just teach there, and I guess some other students from MIT, Harvard, some other schools like that as well. And basically, our goal and our mission is to teach high school students how, to make their own neural networks, everything about AI, basically. So that's what I'm here today, is to talk about neural networks, computer vision, stuff like that, about Spirit AI. So for a little bit of context, hello. My name is Helena Vasconcelos. I am a sophomore at Stanford. Very broadly, I'm interested in philosophy, times X, human-computer interaction, and artificial intelligence. So I'm really interested in studying the psychology behind how people interact with AI agents. So it's that philosophy, psychology, computer science blend. So if you're interested in that, please feel free to reach out to me, because I'm always interested to talk about that. But without further ado, I will share my screen. So first of all, welcome to Spirit AI, or welcome to our workshop for this hackathon. And as everybody's coming in, please feel free to turn on your camera so I'm not staring at random letters on the screen. So thank you guys for whoever already have. So yeah, so today I'm going to be talking about computer vision. So this is the concept behind, and I guess I can present. Okay, so this is basically the concept of making computers see with deep learning. So we'll talk about what seeing actually means. But the outline of what we are talking about in this talk today is first an intro to computer vision. Second, how we actually get from images to numbers, because of course, computers don't actually see images. They see numbers, they see binary digits on transistors, basically. And then we're going to be talking about neural networks, which started this whole boom back in 2012 with convolutional neural networks that allowed computer vision models to be very, very good. And then training a neural network, and kind of getting into some of the details behind how that actually works. So how do computers learn on their own? And so the big question is, so what is computer vision? And so I'm going to start off very broadly, just giving some applications of computer vision. So the big question is, how do we go from the things that we see, the input pixel data, basically from our cameras and our phones and everything, to things that computers can actually interpret. So of course, if you give a self-driving car an image or a video of the outside world, it's not actually going to understand anything unless you have taught it something. And what you need to teach it is the ability to detect certain things, ability to detect cars or stop signs or people, because of course you don't want to be, running over people. So those are very important. And so it starts with this basic concept that humans can look around and see a stop. This is meaningful to us. We understand that. And to drive a car, a computer also needs to get meaning from images, right? If it doesn't actually get any meaning from the thing that it sees, quote unquote, because it doesn't actually see just pixel data, it has to and then understand what this pixel data is, so to get meaning for the computer. And so computer vision is a field of artificial intelligence that trains computers to interpret and understand the visual world. Computer vision is something that I work very closely with. I'm part of the Stanford Vision Lab, so if you're interested in that, also feel free to talk to me about that as well. So I want to first ask you guys, so I'll finally put up the chat, which seems to be very active, but I haven't been reading it. What examples of computer vision have you seen? So Tomas says open computer vision. Yes, I'm looking at these. If an AI injures somebody, who's responsible? Oh, I was talking about this earlier today. I actually took an entire class at Stanford called The Philosophy of Artificial Intelligence, and I had to write this like huge paper, like arguing like who's responsible and like, you know, the whole like AI self-driving car trolley problem. So that's, yeah, there's no right answer. Humanity be overthrown? Hopefully never. As of right now, it's not looking, it's too soon because these models are super brittle, but yeah, we are staring at our screens all day. Humanity is already overthrown by tech. This is kind of sadly true in some cases, but yeah, so Apple Photos identifying people. Yeah, so if you ever pull up your like phone gallery, it'll like automatically identify people and put it into groups. The facial recognition technology, I don't have like a new enough phone. Unfortunately, I don't have like the iPhone 10 or whatever that does like facial recognition for you to unlock your phone, but that's also another application. Moralmachine.net, I haven't actually seen this, so I'll have to check that out. But yeah, so one example of computer vision would be the Snapchat filter, or if you guys are on TikTok, that's another example. I know TikTok filters are super popular, but I'm not really on that so much anymore. Oh, driver-assisted technology, OpenPilot, Autopilot. Yeah, driver-assisted technologies for sure. And so the big question is like, how do these things actually work? Because it has to detect your face and then it has to apply something on it. And so for Snapchat, TikTok, Instagram filters, first they have to detect the face, right? So this is an example of computer vision. Then they also have to identify landmarks. So they have to identify where your eyes are, your mouth is, your ears, or whatever. And then they actually have to process the image by adding graphics. So sometimes this is like relatively trivial, like you know, this dog filter is not super hard to do. But then there are certain things that are much harder, that take something that we call generative adversarial networks, which if you take the class, you can learn more about, but they're just very good for processing images and creating fake images and overlaying things. So yeah, they process the images and add graphics and distort. And so how can we represent an image in color? So images are 3D arrays. They have red, green, and blue pixel values. So the way that processing images as numbers basically works is you have each pixel value that has each corresponding red, green, and blue color value. And then how do you make the colors below using RGB values? So this is not super important for us to kind of go through, but if we wanted to make white, for example, we would make all of the values like 255 because the range of pixel values is 0 to 255. And so it'd be 255, 255, 255, or black would be 000. Gray would be any value repeated over. So it would be 17, 17, 17, 23, 23, 23, or whatever it is. Somebody has to give a presentation. Oh, that's funny. Yeah, and then yellow would be 255, 255, 0, because you're setting the red, green, the Roy G. Yes, I always say it wrong. I always say RBG, which is wrong. The Roy G Biv values. So you would set the red and green values to 255, 255. And then, of course, blue to 0, because that's just how you make yellow from art class. And so we know that each pixel itself has 3 corresponding values. So you have like red, green, blue. And the question is, if you have an 1,000 by 1,000 pixel RGB image, does anybody want to tell me how many actual values there are in it? Just takes a little quick math.
A million.
Close, close. Does anybody have a different, very, 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 okay, yes, 3 million. And so the reason is because you guys are right that you have to multiply 1,000 by 1,000 pixels, but then each pixel has 3 values. So that actually turns out to be 3 million values, which is a lot to process. And one way that we could process this, and then at the end, I'll briefly touch on a different form that is a lot more efficient in processing images. One way that we can process this is neural networks. And what neural networks are really, really good is identifying patterns. And so ideally, what we would want to do is we would want to, pass in our images. The neural network would identify some sort of pattern in the image and then, spit out whatever classification it has. So if we, put in an image of a bird, ideally it would want to detect a pattern of a bird, and then it would tell us that it's a bird. I can talk a little bit more about how in reality we have to use a different form of neural networks, a more specific type of neural networks. But for the purposes of this presentation, I can just talk about this. Neural networks are an algorithm loosely inspired by the brain, and they have revolutionized many fields, including computer vision. And neural networks, basically, the reason that they're so powerful is that they can recognize complex patterns. And the way that they can do this is because they actually learn patterns over time. We don't explicitly tell them which patterns to or not to look at, basically. And so this is just the inspiration. So from biology to computing, we have these dendrites, which are, supposed to be similar to the way that we take inputs. So here on the top, we have like our own neurons, and then we have our computational neurons, and we take inspiration from, having a nucleus in our neurons, and then your terminals, which are basically the way that we output things. And so it's not completely perfect. There are a few things in computer science that we kind of have to smudge a little bit. One example that I will talk a little bit more about later is this idea of propagation, which actually doesn't really have a lot of roots in biology. So we're trying to also, in research, trying to fix that problem as well. But I can talk about that a little bit later. So how does a neuron compute? So very broadly, we have this idea of having inputs, right? And we have to have some sort of weight attributed to the connections between the inputs and the neurons, right? So each input that you have and a certain neuron between the two has associated weights with it. So, maybe if that's certain input neuron and the one we're dealing with right now, the actual neuron that we're dealing with, do not have a strong connection between it. The weights are going to be different between two neurons that do have strong connections between them. So these are learned values over time. And I'll get into that more in a second. And then we have our neuron here, which then has activation functions, and then it outputs things. And again, I'll talk a little bit more about this in a second. So to understand this, super weird concept of what inputs and weights or, whatever they are, very broadly, we can talk about what do you consider when deciding, should I eat lunch right now? Not even thinking about it in computational, in a computational perspective. What would you guys consider if you guys had to decide, should I or should I not eat lunch right now? Okay, Lydia says, am I hungry? Yeah, I would definitely consider that. Terry says, is there food? Definitely. Yeah, you can't really eat if you don't have food. Is the food good? Yeah, that's important for a lot of people. Claire says pizza. Maybe that's super important. Am I doing something currently? Yeah, exactly. So our inputs are basically going to be these concepts, right? Of whether you're hungry, if the food's tasty, if you're allergic to something or not. And so we have our inputs, and here we're going to have binary inputs, just as a toy example. So we have I'm hungry, and we have it set to an input value of 1. So you're saying, yes, I am hungry. And then food's tasty, you're setting that input value to 1 as well. So you're saying, yes, I think the food is tasty. Then I'm allergic, you're setting that 0. So you're saying, no, I'm not allergic. But then we want to set some sort of importance, right? And so this is going to be our weight values. So what do you guys think the importance of the fact that you're hungry is? Super important, not important at all? Okay, so Vincent and Lydia are in agreement that it's super important or pretty important. Okay, so, we might set that to like a bigger weight value. So, something like 5 or something like that. It could be, a weight value. What about food's tasty? Is that important? Less important than? Okay, it's important. Maybe it's not as important, semi-important, as Tomas would say. Kimberly says, yes, important. Yeah, so you guys attribute different weights. So yeah, maybe it's not as important. So maybe it's like at a 3. And then I'm allergic. Is that important? Very important, LOL, Ryan says. Okay, yeah, that's super important. And I'll talk about the differences in weight values in a second. So weights can be positive or negative, large or small. So they act like the slope in linear regression. So this is something that we talk about a lot. And of course, linear regression is also a super powerful tool for prediction as well. And so here we assign the weights like 3, tasty is 1, but here we see -10 to allergic. And it's not that we're not saying that, being allergic or the fact that you're allergic to whatever food you're eating is not important. We're saying it's actually so important that it negatively contributes to the output that you want to eat, like that you should eat. So it's this idea of it should not push you in that direction of eating lunch right now. And that's why we set it to a -10, because it's really, really important, but in the opposite way that you would like to answer this question. And so then you have these inputs and you multiply them by the weights. And then you add them all up to get the weighted sum of the inputs. Okay, so that's very broadly the mathematics behind that. But then we have another term, and we have a bias. And so this bias term, like the intercept in the linear regression. So this would be like the b and y equals mx plus b. It's very similar. And this is also something that is learned over time. And it's a little complicated to describe the importance of bias in other words, but the way that I would describe it is some things do not need to pass through the model. Like when we talk about like neurons in our brains, we don't want like everything that's like all the computations to be like passed through and like everything to, happen. And so some of these connections and some of these outputs have to be quieted down. So what the bias term does is this is something the activation function also is responsible for, and this is something that I'm going to talk about in a second, is the bias term also determines, what gets to pass through or not, as well as the activation function. And so the bias term is adding a value, and that is, again, learned by the model over time, that will say, okay, well, I know that, for this neuron, that, typically whatever output it gets, it's not as important as it should be. So I'm going to add, a 0.2 important for the output. And that'll actually help some more things pass through to the output. Because then what happens is you have an activation function, which then takes output from the bias term. So now we have 4.2. So if you guys remember, we multiplied the input by the weights, and then we got 4, and then we added them all up to get 4, and then we added this bias term 0.2 to get 4.2. And now what we need to do is we have to have this activation, which is really responsible for a lot of this like quieting down of signals that don't matter, right? You don't want to be paying attention to all of the signals and patterns inside of a neural network. That's going to give you a lot of noise. And so what the activation function does, and what this particular one does, which is the max function, is basically says between 0 and 4.2, give me the highest value. And so it's going to give you 4.2. But for instance, if we had, negative 13 outputted by the bias term, then the output would be 0, in which case that would be like a quieted down output of a neuron, because we don't actually need it to then pass through to other layers. So that's also the inspiration and reasoning behind the bias term, because let's say we had something that was previously, outputted to 0, right? Like we multiplied the inputs by the weights, and then we added everything up. And then we added, and then we got 0, right? We got to 0. And then we add the bias term, and then we get 0.2. And then that'll actually allow information to pass through during the activation function, right? Because 0 between 0.2, 0.2 will get passed through, because otherwise you would just have a 0 term. So that's also a reason for having the bias. And so finally, you use the activation function that determines our output, how much of the signal goes through. With the max function, the output can be 0, no lunch, or positive lunch. There are different activation functions. There's like softmax activation and stuff like that, but we can't get into those details. So I want you guys to try this mathematics for yourself. And I know we kind of got through this super quickly. But if you guys will take a second to try this out. So first, give me this first outputted term, and then give me the term after applying the bias, and then give me the final output from the neuron. It's okay if you guys think about it, or I can just like guide you through. Okay, somebody has DM'd me. Okay, I'll give other people a second to think about this. And I can also annotate on the screen, I think, to show you guys how we got to this output. Okay, so some of you guys are landing on the answer. So we have an input of 1, you multiply that by 0.2, right? So that's just going to give us 0.2. And then we have 2 multiplied by 0.1. So that's going to give us another 0.2. And then you have negative 1 times 2. So that's going to give us negative 2. And so that's going to give us negative 16, right? Just doing some quick addition. And then you add the bias term. So you will add plus 0.3, which will land on negative 1.3. And then you have your final activation function, which between the max of 0 and negative 1.3, you're going to land on 0. It looks like you guys already got that. But for other people who might not have. And so now we stack neurons into layers of different sizes. So in this case, this would be a certain neuron. So you would see like this is our input value. And then these are like the weights to that neuron. So to this particular neuron, you're getting all of these input values with all of these weights multiplied, and then all this stuff with bias terms. And then you're connecting them to other neurons. And then you have all these other neurons as well. So this is one layer, and then this is like the second layer. And then we would call these the input layers and then the output layers. I'm so sorry about my poor drawing. And then basically deep learning is adding more layers. That's basically what deep learning is. And so this is the basic architecture of a neural network. And so how can we use a neural network to classify an animal image? What are the inputs and what are the outputs? I want to ask you guys to put it in the chat what you guys think the input would be and then what the output would be, just to check understanding. Okay, so Tomas says colors and features, right? So we would have the pixel values as input, for example. So it would just basically be our image as input, but then all of the pixel values would be their own little inputs. And then the output would be, like Colin says in the chat, that the actual classification. So yes, the input would be the pixel values, and then the output would be the scores for different animals. So a cat or a dog, and whatever has the highest score, you would attribute to the classification. And so how do you actually train this thing, right? Like, how does it just know the weights? How does it know this bias term? Like, that doesn't even make sense. And so we're going to be talking about this. So training a neural network means finding good values for the weights and bias terms of each neuron. And so how do we know if our network has good weights? Does anybody want to guess? Okay, Vincent says we test it. Yes. We need to test how well it actually performs on some input you give it. So when you're measuring a network success, we'll say, given this training data, which network is the best? Which one is the worst? So let's say we have this network 1, which outputs a 1.6 for a cat and 1.7 for a dog. Network 2 outputs a 2.0 for cat and 1.3 for a dog. And remember, I said we attribute the classification to whichever has a higher value. And then finally, network 3 gives 0.1 to a cat and 2.9 for a dog. Which one would you say is the best? Which one is the worst? Okay, overwhelming agreement for 3 as the best. And so which one is the worst? Okay, now we're seeing some 1s and 2s. Okay, we're going to talk about this in a second. So we are measuring by this idea of loss. So loss measures how far the output is from the right answer. So low loss is basically, because you guys already landed on network 3 having the best as the best network. So since it outputs a 2.9 for a dog and a 0.1 for the cat, that's a big difference, right? Like that's a way big difference between the two. And so we would say that this has a low loss. And so it's kind of confusing because loss is a bad thing. So you want to minimize loss. You want less of loss. And so that can be a little bit confusing because it's a little counterintuitive of how we think of like success. So we want lower loss. And then we would say that network 2 actually has a high loss because it just gets it flat out wrong, right? So, you know, it's 2.0 for a cat and then 1.3 for a dog. It says that this is a cat, in which case it's absolutely not a cat. So that's high loss. It's very wrong. And then network 1, we're seeing a few people that said that they thought network 1 was the worst one. And I would normally agree if network 2 were not there, because cat and dog are very close to each other, right? Like they get really similar scores. So we would call this median loss or error. You could think of it as error as well. If your cat looks like that, please take some the vet. Yes. Okay. And so this idea of training your network is just going through your training data many times. So for each piece of training data, you first calculate the output and then working backward, change the weights layer by layer to improve the output. So I'll talk more about this, but the concept is you have an image of a dog, right? So to kind of draw this out, this is my, and please excuse this is my dog. Don't make fun of it, please, or do. But basically, you have this image of a dog, and you put the pixel values through here. And at first, your weights are randomly initialized. This is how we do it in computer science. These weights are randomly initialized. This is gonna be like negative 0.1. This is gonna be like 2. This is gonna be like negative 0.7. I have a really bad habit of always using negative 0.7 something, but you get the point. Just random values attributed to the weights. So at first, the network is going to be really bad. It's going to say cat, definitely cat. Like I think it's for sure a cat, but we know that this is a dog. And And so you calculate the output. And since we know what the actual ground truth label is, we know that it's a dog, then what we actually do is we work backwards and we change these weights little by little. So if we say that this is like negative 0.3, we change it by like adding like plus 0.4. And how we actually change this, how we come up with a value to change it, is by computing the partial derivative, which we are not going to be able to get into today. But it's just some fun linear algebra, multivariable calculus stuff. And so then if you do this hundreds and thousands of times, then you will get a pretty good model, because every single time you're changing the weights a little by little, according to the loss, the calculation that you made. And so that's very generally what you're doing. But how do you choose better weights? The intuition is to take small steps in the right direction. Since we're trying to minimize loss, you compute this loss function, and you compute the loss function with respect to the weights, and taking the derivatives with respect to the weights. And then you change each weight accordingly, very, very small values, little by little, each iteration, each training iteration. And if that's super confusing to you, don't worry. It is a super confusing concept, but basically it's just rooted in a lot of like multivariable calculus and linear algebra. So you're not expected to know how this generally works, but the general intuition is, you have an input, you have like a randomly initialized model, and then you output something. And then since you know what the output is supposed to be and what the model actually gave you, then you'll say, hold on, this is really, really bad. And you go on and you change the weights and the biases, of course. And so that's the conclusion of the neural network talk. If anybody has any questions, please feel free to leave them in the chat and I'll try to get to them. But I wanted to talk to you guys a little bit more about Inspired AI if you guys are interested in this program. So Inspired AI is, like I said earlier, started and still run by Stanford students in computer science, management science. We have some people in like mathematics as well. And basically what we do is we like to teach you guys about, fun things like linear regression, logistic regression, computer vision, neural networks, and the sort. And I also wanted to address something that I said earlier, that neural networks are not the best algorithm for like directly interpreting patterns from images. Those are something called convolutional neural networks, which you also have the opportunity to learn at Inspired AI, or if you guys are interested, looking it up on like YouTube or something like that, there's a ton of resources on that as well. But convolutional neural networks are just a specific type of architecture for identifying patterns in images. So I didn't want to tell you guys that I was going to explain that and then not. So that's generally how that works. So that's super popular in the field. And so, yeah, basically Inspired AI is a program, and there's like two different general forms of how it takes. So we have like during the school year, there are programs where on like Saturdays and Sundays, it's like 2.5 hours a day. On either Saturday or Sunday, it's not both. And then that's for like 10 weeks. For the first half of the program, you learn about like, general machine learning topics. So like what is machine learning, neural networks, of course, natural language processing and all that sort. And then for the second half of the program, you have projects that you guys get to work on in like small groups with instructors. And this is all like, live and online. So you have like a group of like 5 students and 1 instructor. So if you guys are interested in Inspired AI, yeah, we can put more information in the chat as well. So yeah, I wanted to stop sharing my screen. Oh, some people say they're already enrolled in this program. The presentation on Monday is about CNNs. Oh, that's fun. Very fun. So first, I wanted to give any opportunity for you guys to ask any questions either about the program or anything I talked about today. And then we can move on for other stuff that we have planned. Does the training only change weights, or it can also change the layers or the structures of the networks? It changes the weights. That's what training does, at least for a basic neural network. and the biases. Maybe there are really interesting research proposal ideas where it also changes the layers and structures of the network. But yeah, where can we sign up for Inspired AI? Yeah, I can drop our link. It's just inspiredai.com. Did it just start? No, we're starting. Have a program going on right now, but then we're also starting in another 5 weeks for Stanford's spring quarter. So we're on the quarter system, so it'll be starting in April, I believe, like the first week of April. Self-layer adjusting neural nets. Yeah, I bet there are. But for like traditional neural networks, definitely no. But yeah, I don't doubt that people in research are doing really funky things with neural networks and changing all that stuff. So yeah, feel free if you guys are interested to sign up. I also wanted to give an opportunity because this is something like really popular that people like to ask Inspired AI instructors about, is if anybody has, how deep do you go into AI theory and math in your program? Right, so at Stanford, we have probably 60 different classes that are related to artificial intelligence. So it depends on which classes you take. So CS 229 is like the big theory of machine learning class. And that really goes into the math behind neural networks and stuff like that, and computing loss functions and derivatives and stuff like that. But plenty of other classes that are more hands-on coding also make you do that as well.
Yeah, I was talking about but well, that's super interesting. But in Inspired AI, what do students learn?
Yeah, so for Inspired AI specifically, we don't go super in detail in the math because we assume that people are beginners. But if you're put into a more advanced group, your instructor might ask you or might tell you about it.
And you said you were in the vision lab. Mm-hmm. Is it really competitive to get into? Or
yeah. Yeah. Well, I would say so. I think that once you're a Stanford student, then it's better than if you're a visiting scholar or something like that. Because then you can have opportunities with PhD students and stuff. But I've heard of high school students also participating in vision lab stuff and helping. But yeah, I don't know. It's not as common.
Okay.
CS 229 was taught by Andrew Ng, although math is a little different. Yeah, you would need the necessary calculus and differential equations background for CS 229 and statistics. Does anybody have any other questions about that? Because otherwise, I know that usually for hackathon stuff, some people like to ask questions about Stanford stuff, which is why I was talking about AI theory into Stanford, which I like to ask. So if you want to ask about Stanford or college admissions, I'm also here to answer those questions as well, because we also do try to alleviate some of the concerns and questions that people have about admissions and stuff.
Okay. Well, there are a lot of classes available online, Stanford classes. Which one is your favorite?
Well, unfortunately, I always had to pay for them.
No,
But
I know, but like a class that you took that I could find online.
yeah. So a lot of them post publicly their course materials, like their syllabi, their lecture notes, even the code to do their assignments. So CS231N, I can put that in the chat.
Yeah, I'm doing this one right now. So I thought maybe you had another one.
Yeah. So my research advisor actually teaches that class. So I would really recommend anyone who's interested to look at least at the lecture notes for that. It'd be a little bit daunting because it is a very difficult class. So, I wouldn't recommend trying to like do all of the assignments or anything. I know CS230, which is like Andrew Ng's Coursera class, is pretty beginner friendly. So that might be good for people who are looking in, like, just to know about what neural networks are. That might be good. Let's see. CS21 is not machine learning. It talks about more fundamentals of AI. So, decision trees and stuff like that. It touches neural networks like halfway through the class, but it's only like 2 weeks of class, I believe. I'm trying to remember. There's so many other classes. CS234 is reinforcement learning. That's really well taught, and all of those lectures from winter 2019 are online. There's a ton of other classes. CS224N is the natural language processing class for graduate students. All of the ones that I sent are for graduate students, but those tend to be more recent developments in AI, whereas the undergraduate classes tend to be more foundational AI. So, CS131, which is also taught by my mentor, is really, how do I say it, fundamentals of computer vision. So way back when, before neural networks, like how did people think about computer vision, which is still good. Okay, to answer other questions, AI ideas for hackathon level projects. I know that Kaggle is a really good resource for finding different projects that you guys possibly do. So that might be a good place to start. I've never done a hackathon, so I guess I'm not really good at saying what hackathon level basically is. But I do know that a bunch of resources are online about like your first, AI project or stuff like that, because a bunch of data is like widely and publicly available, and a lot of AI is just figuring out what to do with data. Damien says, is there a PDF of the lecture notes available online? Yes. So if you look up any of the course codes I just sent in the chat, and you just look up like that course code and then Stanford, it's going to come up with the website of that class. So on the website, everything is public and available. Stanford has been my dream school for years. Any suggestions for getting there? Be passionate and altruistic. There's no concrete path to Stanford, unfortunately. It's like college admissions is pretty much like very lucky for a lot of people a lot of the time. So I would just say don't just focus on academics, also focus on things that interest you, because ultimately each school has their own thing that they like, and Stanford really likes people who work really hard at things that are like rather unique. So that's like really broad, but I guess I could talk to my own experiences. My thing, riding horses. So I'm an equestrian, and I have been for a few years. And so I took that very seriously, but I'm not a recruited athlete. So I talked about my, accomplishments and things I've done in the equestrian world as part of my application. I think that really helped them contextualize the level of like grit and motivation that I had for doing certain things and achieving certain things. So that's the only true advice that I could give you. Is I would really recommend really caring about a certain thing or many certain things. You don't have to have just one thing, but many things, and being authentic about it, because I know some people are like, oh, this is the thing that's going to get me into Stanford, this is the thing that's going to get me into Harvard, and that doesn't exist. And admissions officers just really look for people who are just genuine, I guess. Do students with little experience in CS stand much of a chance of getting into Stanford? Yeah. So most of my friends in computer science never did computer science in high school. I barely did computer science. I did AP Computer Science A in senior year, and I don't think that they cared. And I would not recommend, like, I know some people are like, oh, well, I can't say that I'm interested in computer science if I'm not like a, level 1 hackathon person, or like, whatever it is. That's not true, because I put that I wanted my major to be computer science on my application, and it didn't seem to affect anything. I don't think they really care that much about it. Can you send me again that course code? Which course code? There's many in the chat. There's a bunch of different. It's all the ones that start with CS. Okay. Does anybody have any other questions? I'm like here to answer any random questions you might have, so feel free.
Can I talk through the mic instead of writing it?
Yeah.
So I won't be going to Stanford. I just graduated from high school. I'm from Argentina, and I know that I won't be going to Stanford because I was rejected. So I'd like to know if there is like a way to contribute to the project, even if like I'm not a Stanford student. I'm really interested in teaching, and I know some stuff in AI. So like, are there similar projects for non-Stanford students that you know of, or something like that?
Yeah, so What do you mean by project? The program?
Yeah, like being able to teach high schoolers about AI.
So I don't think that there's like a prerequisite that you have to go to Stanford. It just so happened that like since it was started at Stanford, a lot of our instructors go there, and they reach out to other people at elite institutions. I don't think that there's like a prerequisite at all. There is a prerequisite though of taking advanced machine learning classes. So I think the application to be an instructor is probably online on our website if you want to instruct.
Okay.
But it does come with the prerequisite of like taking advanced machine learning classes, like the ones I put in the chat.
Yeah. Okay. Yeah, it makes sense. I'm actually like, I recommend the classes by Andrew and G that are on Coursera by deeplearning.ai. They're quite good, especially if you don't know the maths previously. That's pretty cool.
Yeah, it's a good introduction to neural networks. Yeah, or deep learning at all. A few friends worked at deeplearning.ai. Yeah.
Oh, that's really cool. Oh, thanks.
Yeah, of course.
Wait, did you mention what are you majoring in? Since you like philosophy, I thought like that you might symbolic systems, which was it's a great major.
Yeah, it is a great major. So for people who don't know, symbolic systems is a Stanford specific major, which is computer science plus philosophy plus psychology plus linguistics. So I've been in space. Yeah, it's an interesting program. Yeah, I have not declared because I'm a sophomore and I gap year doing research time. So not declared, but I think I am going to major. I don't know. I'm like super conflicted about majoring either in computer science or symbolic systems. It's really hard for me because SimSys is definitely more up my alley, but I'm way more in tune with computer science like classes. So I don't know. I personally intend to major in physics, although I'm considering a computational physics PhD. Do you know any computational physics PhDs? Oh, I'm so sorry, I don't. I wish that would be really cool, but I don't. But I don't doubt that there are people, if you look up like Stanford PhD computational physics, I don't doubt that there are people out there like willing to talk to you. At NSpirit, we tend to have a lot more like computational biology and like neuroscience, which is really interesting. So yeah, sorry. I would been.
Yeah, I'm actually really interested in neuroscience or computational neuroscience.
Oh, cool. Yeah, I think there's a lot of room for AI to mesh more with neuroscience because yeah, like I was talking about earlier, like backpropagation is not rooted in any kind of like neuroscience at all. So Kimberly said, "Oh, bro, you so smart." I'm literally not. I just like read and then I just learn from people who are very intelligent and then somehow that like translates. Neuroscience. Current computational biology. Oh, that's cool. Okay, yeah. So if nobody has any other questions, like we can end here. Yeah, it was super nice to talk to you guys. Thank you guys for having me.
Yeah, thank you so much for being here. It was really awesome to have you here and listen. And it's awesome to hear that like you don't have to like be some insane like guru to. That was kind of.
Totally not. Totally not. Yeah, I would really recommend just like